Okay, thank you. I hope everybody can get a photograph because we took many photographs. Thank you for that. This is a basic schedule that we're going to follow today. So we have presentations for Theme 1 and Theme 2. Theme 1 is about the simple train, and we'll go in this order. So Group A will present first, and each group will have about 15 minutes, not exactly 15 minutes. Do we have a timekeeper or someone keeping time? Okay, so she will show you 12 minutes means after 12 minutes has finished. After 12 minutes has finished, so you have 3 more minutes. Okay, you'll see a sign. And then at 15 minutes, are we going to make a sound or tell them their time's up? Or? Oh, okay, or just announce if they're finished.
Sound is okay.
Okay, sound. Okay. So when you hear that, that's the 15-minute time limit. Okay, so please do your presentation in 15 minutes. After Group A presents, then Group B will present about the same theme, simple train topic, also 15 minutes. After that, we'll have some discussion and question and answer session. And so I hope everybody, while you're listening to both presentations, you can think of questions that you have and some other things you want to clarify. We can talk. And there will be comments from 2 teachers about this theme. And for next, we will go to Theme 2. And this is the sonic velocity study groups, Group A and Group B. Same pattern as this one. We're going to do the same thing. And there will be Group A, Group B, and then question and answers, and then some teacher comments. And at the very end, there'll be a couple of more comments and closing remarks before we finish. So that will be the schedule for today. Okay, do you have any questions? Are you okay? All right, so we can start. Are we ready to start? Okay, so let's start Theme 1 about the simple train, and let's have Group A please come up and get ready.
Group A, and our topic is magnetic train. I'm going to tell you how it works. The theory. First, battery is in the middle, and we put 2 magnets on 2 sides. So the electric current will go like this way. And when the current goes like this way, we cause an N and S on the 2 sides of the coil. And because of the difference between the middle part and the 2 side magnetic field, so it can keep going.
We think factors that affect the train. First, density of the coils. Second, the radius of the cross section. Third, the number of magnets and total weight of the train. We studied about them. Then we are going to show you some videos of our simple train and our maximum angles of our simple train is 63.
So this when we are measuring our how the degree with the train can climb, and this is the experiment we do yesterday.
I'll be talking about experiment 1. In this experiment, we investigated how the magnet affect to the power of the train. So we change the number of the magnet that are fixed on each side of the battery, and these are pictures of the train, and the left side, what you can see is the double magnet train, and the right side is the right train is with 4 magnets, and you can see the figure of the magnetic field and the weight of the magnet.
This is the result. Take a look at the data. This line shows the number of magnets number, and this shows maximum angle. And the maximum angle that so each coil could climb. As you can see, the train with 3 magnets get the highest degree, 63 degrees. And we think it is because the total weight of the train. If we added more number of magnets, the train become heavier. If we then when it's on the slope, it gets a bigger gravitation force. That's why the small number of magnets, 3 magnets, could climb up well.
So after that, after the experience, we discussed about the electric current and the relation between electric current and magnetic field. And we discovered that when the electric current increase, the magnetic field increase too. So we do the experiment is to find the density between the electric current, the relation between the density and the electric current.
So here are our experiment equipments. And we feel the curve of it. We found it was an exponential growth curve.
Okay, so in this experiment, we measure the relationship between maximum magnetic field and the radius of cross section. So we use the ruler to measure the thickness of the coil, and we found that when the coil is thin, it can get the higher magnetic field. But when the thickness of the coil increase, and we can find the magnetic field is going up. But here is strange because when it's got to the thickness is middle, the magnetic field will go down. And we guess this because of the skin effect. And for the skin effect, the skin effect is when our coil is thick, and when our coil is thin, the current will separate in the coil. But when the coil is bigger, and the electric current will just go through the surface of the coil. So it will cause the magnetic field like a U shape. And so this is our conclusion. And we separate the function of the magnetic train. And so here's the push. Here's the force from the magnetic field, and here's a friction field, friction force, and because the train have weight, so it has the gravitation, and with this for force, and if the magnetic field is bigger than the friction force, and the train will go up. So
about the first factor, the number of magnets, more magnets causes the bigger electric field and magnetic field, and the more magnets have more weight. So the conclusion of first experiment is in 3 magnets can climb 63 degrees, the highest degree.
And about the density, we can find that higher density causes more higher electric current, and the higher electric current causes more powerful magnetic field. And so we made a conclusion that the relation between density and electric current is an exponential growth equation. And we analyzed the data by Excel, and we found that it is an exponential growth equation.
So the third one is the radius of cross section. Thinner coil causes a more powerful magnetic field, and thicker coil has lower resistance, and which causes bigger electric current. And conclusion: when the coil is thin or thick enough, its magnetic field will become bigger, and bigger when the coil becomes thinner or thicker because of the resistance.
After that we do an experiment, and we change the length of our coil, and we found if the coil circle contact each other too tightly, and the current will go straight. so it won't go circle. And then, if the current goes straight, the magnetic field will become weaker. So, if its density is too high, the speed will be low. Please wait for a moment.
And this is the video we do in the today morning, and it is in 90 degrees, and it can hold on 90 degrees. It doesn't stuck inside. It is we push it inside, but it can't go up. But it can stay still on in a 90 degrees. And the point is that you can see that we have used a metal. A thin piece of metal brush, and it can brush the magnetic. It can attach the magnet and the battery all time inside the coil, so it won't stop giving the power to the coil. So these are the newest data.
Okay, and this is our presentation. Thank you for your attention and listening.
Thank you very much. Thank you for everyone. Let's go directly to Group B, and we'll continue. And after that, we'll have lots of comments and discussion. Okay? Let's have the next group. Thank you again. Thank you.
The file is rock.
Good morning. So today we are going to talk about simple electric train. And we are students from Senrin High and Kita High and Kaohsiung Girls High School. So this is our context. First, we are going to make an introduction briefly and process the statistic and the conclusion and our future work. So first, introduction. Let me tell about a little bit history of the simple electric train. It all begins in 1922. A German architect called Hermann Kemper, he made the theory, the simple electric train theory. And in 1934, he received a patent for the simple electric train. And in 1970, Germany, Japan, USA, and Canada, France, and England, they started to make a research in it. But in 1970 and 1980, for some political reasons, USA and Russia Federation quit the research. So now there are only Germany and Japan still doing this theory, this research. let's talk about train in Japan. Japan has the fastest train ever. It is 303 kilometer every hour in JR, the company, JR company. And it also received the Gennomian record in 2015 and 2013. And in 2015, in April, they claimed that they are going to build a road in 2027 from Japan, and in Japan, from Tokyo to Osaka. And it only takes 40 minutes if it's done. So let's look forward to it. So, okay. And now let's introduce our needed materials.
How can we conduct this experience? So we need this material, and you can see magnet and battery and copper wire, and we have many different kinds of thickness of copper wire. Yes, and this is our. We have different size. You can see number 7, number 9, number 10, and the different of kinds of magnets. And our experience, the number 9 magnet is the best one because number 10 is too heavy, just like a dumbbell, yeah. Yeah, and this is our battery, and you can see this one is, of course, it can't use because the shape is square.
Okay, so when we got the copper wire, and then we need to make it into coiled copper wire, and that is like this, and it will become like this. And then so we will show you the whole what the whole electronic device will look like, which is like this. Okay, so then we will put this one into there. Okay, so we'll show you the video. So simply it's just like this way, and it will just run. And we are going to do something like that. Okay. So let me show you how it works. So and then okay. So this is the picture that we got, and this is the okay. I will show you simply like the scientists didn't really know the connection between the magnetism and the electronic, but they still it's when the magnet and batteries is put in the coil, then it will conduct a magnetic field, and then so simply look at this pictures. You can see that when it is pushed right on the right, sorry, if it is pushed on the right and then it is pulled at the left, then it will be like, it will repel this way and they will attract in the other way so that it will move forward. So this is simply how our train works, yes. And so this is just simply like it will attract by north, different poles will attract and same pole will repel, yes. And the next one we are going to show you is that on the other side, when you reverse your magnet, then which is like different from the last one, the NS one, and you just reverse it and then you will move it in the opposite direction. And then the next one is that, sorry, this one is that it wouldn't move. Why? Because when you got here, this is like it's the same. It's a different pole. So the different pole will attract and it will push this way, and this will also push this way, like this. It will push, so it wouldn't work. It would just like attract, and then it would just stop there. Yes, and so it wouldn't move. Okay, so we're going to show you the experimental condition, which is like we got five factors, which is the thickness of the coil, the type of batteries, and the number of magnets, and the numbers of the left and right magnet. And when it is like we got 2 batteries and we connected with different amounts of magnets on different sides and in the middles. Okay, so okay.
change thickness of the copper wire and the thin one is faster than thick one. And next, change different type of battery and AA battery is faster than N type of battery. Third, we change number of magnets. Results. The more batteries we connect, the faster it moves. Fourth, the rate of left and right magnets on battery. Results. The smaller the difference in the number of magnets at both ends, the faster it runs. Finally, linked batteries and magnet combinates. Conclusion: the more magnets on both ends, the faster it runs.
So I will do the conclusion of the combined 5, which is like if you want to move the fastest, you can get the battery type of the 3A ones, and then if you want to make it move the fastest, the thickness of the coil should be narrower than narrower will run the fastest. And the third one is like the number of the magnets on the both sides. The more the battery is, the faster it will run. And the fourth one is like the different numbers of the batteries on the batteries, and evenly it becomes the faster it runs. And the fifth one, simply you can just imagine that it is the same as the third one. So it is like the more the battery, the more magnet is on the batteries, the faster it will run. Okay. So later we are going to have some discussion about the angle of the heel, and then.
We change sharp or hot this coil, this the thickness. So the sharp one move better. Okay. Change battery.
It's like when you got different volt, VOT, then when it becomes like the 6 or 12, it wouldn't even move. Why? Because when you know that the batteries, the 12V ones, it's connected with 5 little batteries, and when you got 5 little batteries together, it will just repel. And it's just when you try to measure the volt, then it wouldn't even just the device wouldn't even show, because it's not even current. Yes, it's not even, yes. Okay, so this one.
we change the battery voltage of the battery. The little one is the lower voltage. It goes up to the 45 degrees.
We change interval. We change interval. Change interval, so it moves up 80 degrees. Great.
Let me simply show you what the interval is. So when it comes to the 0 centimeters, it will be like, it will just like this height. And then when it becomes 1 centimeter, it will be like something like that. So this is like we combine two conditions, which is the interval is whether the interval is 0, and then we use the volts to try it. Then we can try it up to 45 degrees, and with the batteries of 1.5, which is the 3A's batteries. Yes, and then this one is when it comes to like 1 centimeters of the interval. Then it will also be like it can also run to 3A batteries, and it can run up to 45 degrees. And then special thanks to our teachers. And yes.
So I want to mention about this teacher. Although he's not here now, but we want to pay our respect to him. Yeah, so good luck in your military life.
Thank you.
Okay, thank you. So we would like to have some discussion time and some questions and answers. So both groups, Group A and Group B, about the train can be involved. So I think this is open to everyone. So let's ask anything you need, any questions you have. So from the other, yes, Leo, should we pass the mic?
So I want to ask about skin effect that you mentioned in your PowerPoint. And you just said that skin effect is the phenomenon that when a current runs through a different radius, the different radius of wires and the way that current runs through it will be influenced. So I want to know the reason that behind this phenomenon. So can you just explain it for just in a simple way?
It is because the magnetic field, and because the coil, if the coil is thick, and if the current separate average, there will be a magnetic field inside. And you know that the magnetic field will be here's the because inside has magnetic field and outside has magnetic field. So the distance of the center to the surface is bigger, so the magnetic field will be bigger, and it will
like it will the current inside will be minus from the outside, so it will cover the current because of the magnetic field. So you know what I'm talking about.
I think I know, and so so I would think that this phenomenon is produced by the magnetic field that's produced by the current itself. So the current which runs inside the coil will be repelled by the magnetic field, so it will be reduced. Is that what you mean?
Yeah, it all happened inside the coil, and because the coil is big, so it can do this. And but if it is thin, the distance from the center to the surface isn't so big, so it won't it won't have the yeah.
Okay. Thanks.
Thank you. So you tested some things and found some limits. I noticed that both groups found some limits. If we keep making a bigger coil, it gets better, right? Oh, no, it doesn't. There's a limit. So that's very good that you checked that, and good question. Let's ask more. Anything you want to either group is okay. Yeah. Oh, thanks.
To Group B, am I allowed to see your data about the range of the circle, triangle, and like arrow you make on the you make on PowerPoint?
Sorry, can you repeat your question?
Just am I allowed to see your data about the range of the circle, triangle, or arrow? Because I'm not quite sure what that stands for. Which red? What?
What is the circle, triangle, arrow means?
The
Data?
yeah.
This one? Alright. So the circle means it moves. And obviously the cross means it doesn't move. And the triangle means it stopped there. Right. Any questions? Number? Where? Which one? Oh, this is Newton. Newton. Yeah, the force.
To Group B, I want to ask a question. Does all the results from the experiment match the Lorentz force?
Can you make the specific noun, pronounce it again, or?
It's just like the definition of the magnetic field and the force.
I think it does.
But do you concern about the friction of the coil, or do you measure all the
So actually the force, the maximum force is like the mg sin theta plus the friction. When it's the maximum, the mc sin theta and the friction comes to the same width. But when it's the minimum, the mg sin theta and the friction comes to a different width. So it will come to a minimum force. Do you get it? Alright. Any question?
You can ask either group. It's okay to ask anybody.
Teacher
Yang Huan.
Do you want to ask any question? Oh, show our page. Show our page. Yes. our teacher, Yang Huan.
Thank you. Did you have a question or anything? Not yet. Not yet. Yes. You have a question?
Can you say about your theory again? Your theory.
Actually, our theory is affirming right-hand law, but we didn't put it on because it's. So simply, you can just see that when. So what the whole scene moves, it's because of that. It attracts and it repels this side. Yes, you know that when we are trying the magnets, then we have like both magnet and we have to make it repel on the both side, right? Or can you explain how you put on your magnets? How you try to put on your magnets?
So do you think the train moves because of the two magnets on the two sides?
It's because of that when we got to research that the battery simply is a. You can just imagine as if it were a magnet bar, and then so because of the repel and the attract and then with the coil, so then you can see that it move forward. Because of yes, it's of course it's because of the force which puts it. What? Yes, this is of course one of the factor, right? Or you guys, what factors did you get? How did you really move?
I think it moves because the electric current and it caused another magnetic field.
Yeah. But this is how you got to make the magnet and the batteries to have a current right before the. So as I just mentioned about, I talked about the Fermat's right-hand law, and this is one of the factors that is expect for the Fermat's right-hand law. This is like the two factors of how it moves, but we didn't put it on because we don't have really much time for it. So maybe we will do it as a future work.
Okay, thank you.
We have a few more minutes, so please ask anything else. Questions or things you would like to clarify?
I would like to encourage Japan students to say something.
Yes, me too.
Because I don't want this to become a battle between. I expect very strong relation.
This comes back to the basic questions, right? Why does it move? Why does it move? What's happening? You can ask any questions about that to either group.
We just came up with the question for group A. Like, what is the equipment you used yesterday? Can you explain the theory or something?
Yeah, you can use this microphone. Equipment that you use.
And what?
Which
还要我们示范吗？哎，可我有在那示范，帮我。
Sorry. You can complete one.
Sorry, can you repeat your question again?
Simply, we just want you guys to explain what that is because we are really interested in that one.
Okay,
Because we don't have.
we can show you how we measure it.
So here's the couple.
Please.
Sorry.
We won't fight you, okay? No fight.
Okay, so that's the copper coil from Japan, and because their copper coil is very, it can make big current. So we use their copper coil and their magnet and their batteries. Yeah, that's all from Japan, and it can move very smoothly. And our school has bring here's a machine from our school, and it can measure the magnetic force and the current with this current tester and this magnetic field tester. Okay, so we now put our train inside the coil. Sorry.
Table.
Yeah, the table. One minute. Okay. So the coil has been a little bit broken. Yeah, but although the coil is a little bit broken, we can see the the magnetic field of the coil when the train passed by. And so we didn't connect on the current tester, but we can see the magnetic field. It will increase when the train goes through. Yeah.
If you want to try it one more time, then we have to. Here we go.
Okay. Yep. Okay, so here. Okay, so we can see here. When the head go through, the magnetic force will first increase, and this the body that is and here's the body part that is the battery, and so the magnetic force will go down, and another is the tail, the back of the train, so it will increase again. So it's the full. Yeah.
So you got a peak on the reader, the graph, peak, and
Yeah.
back and the head and the tail.
So if you want, maybe you can use the whiteboard here. Okay.
It's okay to use the board. Okay. Maybe the more you look, the more questions you think, right? So more questions will come up. But we'd like to get some comments from some teachers now. We have two teachers to make some comments about this theme. I'm not sure who wants to go first. Okay, here you go.
Okay, thank you for your presentation. I really enjoyed your presentation. And first of all, please do not fight during the discussion. It's just advice and just a question. So Q&A makes your project better in the future. Okay. And then I have some questions for each group. So for group A, how many times did you try? Experiment. So you showed 63 degrees was the maximum, and second one was 59 or something. So I don't know
the only 4 degree is big difference or not. So you did just once, or you tried many times. Is it just error or it's the difference?
We increase the angle 1 degree, 1 degree, and to the maximum, it can move to the top. And if we can move to the top on the next degree, then we will choose the next one for the maximum.
So you try it for how many times? One time?
Many times.
So you try it every time, again, again and again. So
Maybe if we start on 60 degrees, then we will try 60. If the 63 degree succeeds, so we move to 64, and then if the 64 fail, we will try 63 once again.
Yeah.
Then we'll do this many times. We repeat it many times.
So that is one time. Actually, that is one time.
No. We have the 64 degrees. We have seen 4 times 64 degrees. Yeah, but it's a little difficult to be 64 degrees, but it goes 4 times. Yeah, actually, we have to do 4 times.
So you have 4 times.
That's it.
Actually, we did it tomorrow. This morning at 6:00, we went to school and got it.
Okay, thank you. And for group B, I think you need the number, just only the symbol. So this is science, so you need the number of the. Yeah. You have to think about how do you.
Everyone wants to know.
Oh no, see? And many number. Yes, because she's 1, she's 2, she's 3.
Okay, we can maybe okay later. Okay, thank you.
And they calculated, yes.
So I think this theme is very interesting, and so I think you can continue your project after this session. So please think well the theory and why it works and what cause it. So thank you for your presentation. It was really interesting. Thank you.
Yeah, I think a lot more questions keep coming up, so that's what's supposed to happen. Thank you. We have more comments from another teacher, right? Okay.
Hello everyone. I think two groups have a good presentation. You are good to express what you think. And I also want to add some questions and some suggestions because I think Group A is very good at both grade to draw the relationship between curve and the density of coil. I want to ask the last one. The curve is like this. Can you show this curve? Yes, thank you.
Yeah, maybe you can show.
Yeah. Show it again quickly and explain it one more time.
We have the file. We have the file here. Right?
no, sorry. Magnetic field and the thickness of ray.
This?
Yes. I want to ask how to explain why the 1 millimeter coil is the lowest magnetic field, because skin effect, and why after because above larger than 1 millimeter its magnetic field will arise. How do you explain it?
Okay, because in here we can because the point effect the current is 3 points. One is the skin effect, and the second is the resistance, and the third is the thickness. Okay, so because of it's very because when it is very thin, and it will attach when we.
So your main question is about this side. Why it will increase is because when your coil is become bigger, the resistance become lower, and resistance become lower when your voltage is same. The electric current will become higher, and from the results we do in experiment 2, the electric current become higher, the magnetic field will become higher. Then the magnetic field become higher, the force that increase in the magnetic field is bigger than the skin effect that's decrease in the magnetic field. So it will still increase, but it will not increase as fast as the thin side.
Because there are so reasons to miss to affect this phenomenon. So I think maybe it's a point to affect most. Yeah, that's why I want to ask. Thank you. And for Group B, I think just like the teacher said, I think you have to quantity your experiment result will more clear. Okay, and I think it's for 10 minutes, so I forget what I want to ask. It's okay. Let me ask for private. Yeah. Thank you.
Yeah, I think there's not enough time to ask all the questions, but thank you. Okay, thank you teachers for your comments and questions. And we'd like to continue. So we'd like to go to the next theme, which is theme 2 about the sonic velocity. So could theme 2, Group A, please come up and get ready. Thank you. Okay, please come up to the front.
Is it too cold for you? If it's too cold, raise your hand. Cold. No?
Okay, they're ready now. Let's listen.
Good morning, everyone. We are Group A for theme 2, sonic velocity. And yeah, these are our team members, and they're sitting over there. And my name is Paul, and this is.
Would you please use the microphone?
Oh.
Oh, okay. So, sound propagation in narrow tubes. There really isn't any like daily applications we can use it for. Well, yes, in 1950s there were computers made using these things, but yes, it's like in the 2000s now. Nobody really uses narrow pipes and sounds to make anything. And how the presentation will work? Well, first off, I will start off with a short introduction of what the theme is, and then I will hand it over to Japan, and then Japan will go on and talk about their theory and their experiment, and then it will come back to me to talk about what Taiwan did. Yeah, so let's begin. So the challenge was this. Sound propagates slower when moving in a tube. Investigate this phenomenon and determine the parameters that may or may not affect this event. And yeah. So here's a short video of what it is. Okay, you can't really hear sound, but in the video there was like sound. So there's like a guy hitting a thing on the side, and then there are two microphones at each end of the tube. And then we measured the delay in time for the two microphones, and then we can see how fast sound moves through the pipe. And according to theories, it should move slower, but yeah, you'll see later in the presentation that this really wasn't the case. So if you really still don't understand what the thing is, here is a list of emoji for you to like look at. So sound goes through narrow pipe, and sound will become slower. Yeah. Okay? Yeah.
So our group measured sonic velocity through two processes, and I'd like to talk about one of them. And our experiment is based on this formula. This formula shows the relation between the sonic speed and several following factors. Thank you. The formula is A times brackets 1 minus 1 over R times square root of mu over 2n low. And the factors that affect the sound is included in the formula by alphabet. And well, A represents the speed of sound from outside the tubes. R is the radius of the tube. Mu is coefficient of viscosity. N is angular frequency, and P is the density of the tube. Well, I think most of you are quite confused of this formula, but don't worry. Actually, in our experiment, only the radius and density changes, since we have only changed the materials of the tube. Oh, by the way, this whole formula was founded by Helmholtz, who was one of the greatest scientists in the 19th century. So we moved on to our experiment, and to conduct the experiment, we were required with some equipment. An oscilloscope to enable the observation of the sonic speed. As in the picture, you can see that the sound is showed in the forms of waves. Also, quite a few number of tubes made from copper, aluminum, and brass were used to slow down the sonic speed. They are in different diameters with 2, 3, and 4 millimeters. Last but not least, highly intelligent microphones. These ones were used to, in order to perceive the sound. Next, I would like to talk about the experiment results. From the top, the graph lines represent the results of aluminum, brass, and copper tubes. The horizontal axis here stands for the diameter of the tube, and the vertical axis shows the percentage of sonic velocity. As you can see, aluminum shows the biggest as you can see, copper shows the biggest decrease in speed. When the sound goes through the copper tubes, its speed decreases by almost 3, 5, and 6%. All three tubes' sonic speed gradually slows down as the inner diameter becomes thinner. As I just said, the thinner the diameter is, the slower the sound will become. These results matches the formula I've already showed in the former slide. This one. Low represents the diameter, and if low becomes smaller, then since it is in the denominator, this whole fraction will be bigger. And therefore, the number and the square root will increase. The number in the brackets will become bigger, and it will become smaller actually. And as a result, the whole number decreases, which means sonic velocity occurs. From the results, it is quite self-evident that the formula shows the correct relations. And now I would like to pass on to Paul for the second process.
So you can see that this is ridiculously complicated, and our theory is also ridiculously complicated, so we couldn't really put them together. So yeah, let's start with the theory first. So there was one main parameter that affected what we thought affected this phenomenon. So it's called the shear wave number, and we'll use S to represent it. So it's the ratio of the inner radius of the tube to the viscous boundary layer. Okay. So what it basically is the viscous shearing effects of the wall. So yeah, that's what it is, and that's what affects this entire phenomenon. Yeah, so ratio, blah blah blah. So this is how you calculate the shear wave number. So S equals R times the square root of omega divided by mu. So the R is the inner radius, and this is the viscous boundary layer, which is that. Yeah, so mu stands for viscosity of gas and angular frequency of gas. And since all we use is air, the viscosity of gas doesn't change because we don't change the gas. So that stays as a constant, and the angular frequency of the gas, since we only use a single tuning fork and with a single frequency, we can also determine that. And yeah, we can use 2 pi f to determine the angular frequency of it. And yeah. So this is the formula that we use to calculate the speed of sonic velocity, theoretically. So, okay, whatever. Do you want me to read that? I can try. So square root of so J0 and J2 are basically kinds of equations, so you throw a number in it and it gives you another number, and it throws a number out. So that's just like a process that we use, and yeah, it's very complicated, and we're not really sure how we can calculate it. And gamma stands for the ratio of specific heats, which is it's basically the ratio of specific heats of a gas, and since that gas doesn't change, that number stays the same. We use 1.4 since it is air. And yeah, it's very complicated. So we use, okay, whatever. So we also need to define the thermal boundary layer thickness, which is that, and that's important. So basically, we use it to find sigma. We use it to find this, and because everything cancels out each other, and then what we get at the end really doesn't depend on anything we change. Like, we don't change any of the parameters that affect this, so that stays as the same number. So all we need to do in this experiment is to find S. Yeah, so it's independent of viscosity, so we don't need to do anything about that. So once we get the gamma, once we get the number from the ultimate formula, we take the imaginary part of the number we get, and then we take the free space, like the sound in free space, like not in narrow tubes, in free space, and we divide it by the imaginary part of gamma, and then we can get the velocity of sound that should, it should be that. But yeah. So no numbers are that we know gamma, we know that. So the only thing that we need is this, because that's just like a function that you can use. Yeah. That's. So things we should test for are the inner radius and the frequency of sound. So the experiment. Apparently the topic tells us to find like 4 millimeter thick tubes, but we couldn't find any, so we decided to use extremely big tubes. So the first one is metal, the second is aluminum. Yeah. According to our theory, the material doesn't really matter, only the inner radius does, so that's where we differ from Japan, and we're not really sure which one's right or which one's wrong. So yeah. So we use the tuning fork to produce the sound. And also we couldn't put the tuning fork inside the tubes because the tubes were too small, so we had to hit them outside. So that's where one of the major errors came in. We weren't sure if the sound was traveling through the tube, in the air, or like inside the tube. So we couldn't really see if our theory was we couldn't really see if our experiment was entirely accurate. So this is what we use to measure the delay in sonic velocity. The two microphones connected to a machine called LabQuest 2, which is awesome. Yeah, the microphone, and LabQuest 2. And at first we did, no, I'm not taking a picture of the bus. At first we did have the equipment, so we tried to use earphones and a program called Audacity, and it actually worked out pretty well, but then we got like more sophisticated equipment, so we switched out and opted for the other one. So here are some stats for each tube. For the copper, this is all in meters, so it was like 2 centimeters, the radius was like 2 centimeters, 1 centimeter, 1 centimeter, and 2 centimeters, and this was like 0.36 or something like that, yeah. It was like 0.36. So then, as I said before, the formula was too complicated, so we used Wolfram Alpha to calculate all our results. So basically, we threw the numbers in Wolfram Alpha, and Wolfram Alpha spitted the numbers back out. Yeah, this is like the example of what it spit out, and then yeah, it's very complicated. So this is S, and this is sigma, square root of sigma, and that is the gamma, and J2 and J0 are very complicated Bessel functions. So after we threw the numbers in, because we know the frequency of sound, and we also know the inner radius, this is what we got. For bronze, you can look at the numbers yourself. So we took this part of the number, and then we took the speed of sound in free space, and then we divided them, and then this is what we got. As you can see, most of them are like not exactly the same, but they don't differ a lot, but you can see that as the inner radius becomes smaller. This has the smallest radius. The speed of sound should technically become smaller. But this is our experimental results. For the green pipe, yeah, this is like a part of our experimental results, and as you can see, sometimes inside the tube the speed goes faster for some reason, and that wasn't really what we were trying to do. But these were our results, and it's slightly slower, but the results were all that good. So this is like a sort of like a line graph. So our theoretical, you can see, is basically just a line, and it shouldn't really change. But in our experiment, it was a zigzag, and we're not really sure what causes this. Maybe it's our testing ways, or I don't know, our tubes. But this is what we got. So surprisingly, the errors weren't that big. For the metal thing, we only had a 5% error, and then for a super thin tube, that's a tube. Like it's a pipe, and there's something like it's empty inside. The error was only like 9%, so it wasn't really that big. Yeah, so this is everybody in our group. Yay! Thank you.
Okay, thank you very much. And you did a Japan side and a Taiwan side, and you put them together, or you tried to put them together. So we'll be able to discuss that later. Let's go to Group B and have the next presentation. Thank you. Are we okay to start? The time is okay? Okay, go ahead.
Hello everyone, here I'm going to introduce my teammates and I will introduce the delay of the sonic velocity. And before talking about our experiments, I would like to talk about the theory so that you guys can get some ideas of what we did with this topic. Otherwise, you may just fall asleep like I usually do in my math class. Okay, and the first theory I'm going to talk about is the Reynolds number. This proper noun got its name from the English scientist Osborne Reynolds. And this formula shows how to calculate the Reynolds number and shows the relationship between Reynolds number and the factor. So for example, Reynolds number is when Reynolds number increase, the density, velocity, and diameter also increase. When Reynolds number decrease, the viscosity still increase. Why is Reynolds number so important? That's because it's an index for us to identify the flow we're going to observe. So if the Reynolds number is less than 2,000, then we call that laminar flow. And if the Reynolds number is more than 4,000, we call it the turbulent flow. And if the Reynolds number is between 2,000 and 4,000, we say that the flow is in the transient condition. And also, I want to talk about viscosity, which is another factor to affect the Reynolds number. We use viscosity to describe a fluid, how it flows. Let's take water and syrup for example. Water can flow more easily than syrup does. So we say that water has a lower level of viscosity. And this picture shows us the relationship between the bond and the viscosity. As we can see, water has a weaker bond than the chocolate syrup does. So we say that water has a lower level of viscosity than the chocolate syrup does. And then Connie will talk about the flow velocity. The left one, this one, is without friction, like this. And the right one is with friction. The velocity of the fluid in the middle is the max. In the laminar flow, the fluid along the wall here is the most slowly because there is friction. From the fluid along the wall to the one in the middle of the pipe, the velocity increased by degrees. As to this one, turbulent flow, the velocity still increased by degrees, but the fluid in the middle of the pipe here doesn't flow as quickly as the one in the laminar flow because different layers will influence each other. And Hanaka will introduce the length.
And we use microphone, aluminum, steel, copper, glass, plastic, and an oscilloscope, and low frequency oscillator, like this figure. Next, you tell you about experiment.
Sorry. We know this formula. K means bulk modulus, rho means density, and C means velocity of sound wave. Each material has different Z's. As a calculate, we can make the real quality clear.
For our experiment, we could get this data. Please pay attention. The pipe is narrower. The reliable quality is longer. According to this graph and this graph. Next, presenter Yurika will talk about the reason of a result.
To do the experiment, we bought long pipes, so we need to cut the pipes. But to cut them, we didn't use any machines. We used tools like cutting knives by using hand. So the cut edge become rough than usual. It connects to ease of reducing speed because when enter the wave of sound into the pipe, the rough area makes the direction of wave disordered. So the wave of sound attacks the wall of inside of the pipe more times. That means the friction generates more times. Next, Grace is going to talk about other results. According to the graph, we can find out that no matter how long the pipe is, the sound velocity in the aluminum decays the most except the 30 centimeter one. Besides that, there's an accidental error. We found that the aluminum's friction coefficient is bigger than the copper's. That cause friction between aluminum and floor is bigger than the one copper and floor is. As a result, the sound velocity will decay the most in the aluminum pipe. And next, Hanami will talk about the third result.
In general, we understood that 5 centimeters of all the 6 materials made the sound slow. Next, we compared 4 thickness of the aluminums, which were 3 mm, 5 mm, 7 mm, and 9 mm. We understood that the thinner they become, the slower does the sound travel.
This is reference. Thank you for listening.
Okay, thank you very much. Thank you. Yeah, okay, you can sit down now. And we'd like to have question and answers again, so please don't hesitate to ask anything to either group. Great. Okay.
For Team A and Team B for a great presentation. I have question to Group A. Group A prepared material, then plastic pipe, then you showed green pipe and gray pipe. Are these plastic pipe, and what the difference?
so according to our theory, the inner radius is the thing, like the only thing that affects the speed of sound. So we weren't really like testing for the material, so we aren't sure if they're like the same or different. What we know is that the inner radius is different, and yeah.
Thank you very much.
Okay, this is why we have two groups studying the same topic. The other group had a little bit of difference with the different material, and you guys thought that there wasn't maybe a difference, so you focused on other things. So, yeah, good question. Let's have next questions. Any questions? Okay.
I have a very simple question for either group. Is there any application for your research?
Yes. Just like the beginning of our presentation, we said that about decades ago, the computer used this kind of phenomenon to store store memory and information. But nowadays, I think it is mostly used in professional fields.
How do I store memory data by using this technology?
Now we should turn the question to Wikipedia.
After reading, there's like a Wikipedia page called Sonic Delay Line. If you want, you can go on there. So basically, there's like they fill a tube with, and it's also not like exactly the same as our topic. Like they didn't have like an empty thing. They filled like a tube with mercury, and because sound moves like a little slower in mercury than it does in like somewhere else, there's like a delay, and they use that delay to like shoot out pulses or something, and then the delay and pulses can like then be turned into like electrical signals, and then it can be used to like store memory.
Okay, so there's a very practical use some years ago. Maybe now computers are run differently. Okay, I think there are other practical applications, as Leo asked, because you were talking about the friction of the, where did you go? You were talking about cutting the tubes with the hand tools. Right? So when you cut the tools, you got a rough surface, and that affected the air flow. So it seems to me that there are many effects of that. So even if you're not only talking about the little tubes, you're talking about the things that you study in order to understand this topic. I think you have many practical applications. So you found some. Questions? Next. You can have questions or comments. Yeah. Okay, teachers as well. You have any questions?
May I ask Group B and your result 2, the slide, what's the y-axis and the x-axis and the physical meaning? Would you please show us the result 2? Yeah, what's the x-axis and the y-axis? What's the meaning?
Oh, this is the x-axis is the length and the y is the decay, the attenuation ratios.
Length of the tube?
Yeah, this one is the length of the tube.
So the y is the delay, the time of the, I can not really understand the unit. What's the unit?
It looks like MMS.
Minutes.
Minutes.
MMS.
Minutes. Is that right?
MMS.
Or is that millimeters per second?
Yeah, I don't know. Yeah, maybe meters over millisecond or millisecond, or I don't know. Millisecond. Okay. Yeah. Thank you.
I think teachers or students can ask or clarify something. Yeah.
So to group B, so did you actually get like theoretical results? Like from your like theory, did you get a number like how fast it should move in the pipe or something like that? And yeah, did you compare it to like your experimental results and did they match?
Yeah, they do match because we found because there's a formula that F equals mu s times n. So we found that aluminum's the coefficient friction of the aluminum is much bigger, not much bigger, but bigger than copper's. So actually, the friction along the aluminum pipes wall have to be bigger than copper, and that's why it will decay more strongly.
So that matched the theory that you. Okay.
Sorry, maybe I misunderstand your slide because I think, so you mean the length will affect the velocity delay or?
This is like when the length is 10 centimeters, the three materials will go like this. The aluminum, the annihilation ratio is the aluminum is bigger than the steel and bigger than the copper. And this one is in 15 centimeters. The ratio is aluminum bigger than steel and bigger than copper. And this is an accidental.
Sorry, so how can you define your attenuation ratio? What's attenuation ratio? Means the time delay or the velocity after your calculation, so you can compare with.
We did the calculation to find out that the time when is like the calculation is things that we did the calculation and about the time, so we can see that we have like A speed, B speed, C speed in aluminum, and we will use B to minus A.
Yeah. Okay. So I think I can understand you. So can you show me your C equals the bulk modulus and would you please show the slide? Yeah. The velocity of the C equals root. You know you.
C means basic of sound wave.
Sound wave. Yeah.
You had a slide.
Yeah. So can you tell me what's the difference between the? In my opinion, this is the air velocity of the sound, but what's different from the copper and the material? Will affect which one? Or you mean, maybe I don't know what you're going to show us. So you mean the equation is affected by the material?
C means the velocity of sound wave. But we think according to this changing delay of quality also changes too, we think.
Yeah, so I feel confused about the topic is you have to measure the sound in the tube by the air through the tube, the velocity, or you mean the sound just transferred by the material?
We can measure the delay of quality from oscilloscope, but we couldn't measure the velocity. Yes.
Okay, so would you please tell me what's your device? How did you make your device?
Device?
Yeah, you measure the velocity through the air or through the material? Yeah, I know, but I have, because the tube, if you measure the the sound goes through by the air and goes through by the material. That's totally different. I want to make sure which one you measured. Because they say that the material did not affect a lot, but your data shows that does affect, right?
Right. Oh yes. Changing the materials, also the wave shapes really changing. So we think the changing materials is the important keyword of about the quality of sound wave.
Yeah. So you mean the material change the wave shape, right? Wave shape or
too. Wave shape too, and not wave shape, but
or the viscosity. Or at first you show us the viscosity and the radon number or something. Is the material affect the viscosity or the radon number?
Yes.
Yes. Okay. So how about you? Do you think you say that the material doesn't affect the velocity? And what's your opinion about the explanation, or do you have any explanation for your results?
Excuse me, I would like to do a small explanation. Is that this pipe is hollow, so outside the pipe is like aluminum, or it has different materials, but inside is the hollow. So the sound speed still go through the air, but it will has friction between the air and the pipe.
Material. Yeah. No. Yeah. That's good. Yeah. So I understand your experience. So you really you the same. You measure the sound wave from transferred by the air, but the material will affect the viscosity. Yeah, I think that makes sense. Yeah, okay. And how about your explanation or your thought?
So the two main things that we focused on was the frequency, because if the frequency. So if we think that the frequency and the inner radius is what affects it, we didn't really talk about the material, but I don't know.
Maybe you have some ideas, right? I mean, students in your group.
In our idea, and the viscosity affects the speed of sound in a thin tube, because in our formula there is the value of viscosity, so I think the viscosity affects the speed of sound, I think.
So more than the material, it's the diameter and of the tube.
Yeah.
More than the material. Material is not so important.
As much as.
Not as much. Okay. That was kind of a good question. Yeah. Good. Okay, we have a few more minutes. We have another question.
Teacher first.
No, you raise your hand first.
Thank you very much. Group A and Group B, both of you, thank you very much for a good presentation. I'm a teacher of mathematics, so I'm interested in formula. I'm very interested because each group use different formula. One group A used formula made by Helmholtz. I heard Helmholtz as thermodynamics, excuse me. And on the other hand, Reynolds number group B used. I heard the name of Reynolds as fluid dynamics. So each groups use different formula and different method. I'd like to, I want to know the reason why you choose each method or formula.
both groups can answer. You want to start? Okay.
I think we probably use different perspectives to measure or to calculate the sound of the velocity of the sound. In our group, we use thermodynamics, and in other groups, I think they can use force or other elements to measure the velocity of the field.
Okay. How about the other group? Yeah.
I also read Helmholtz's book, but it is so difficult, and I found the formula, I think, so very complicated. So I decided I can't understand that formula. So I made another book. It's so easy. So it say, if you are a monkey, you can understand. That's what it says. So I did, and that's so easy formula. It is also tonic velocity formula. That's so common. So I use a common formula. Thank you very much.
Okay, thank you, and an excellent question and answers.
You want to add something?
The reason the reason we select it, the methods is we think that method is very simple, and we can watch the wave by the oscilloscope clearly. So we selected that method.
Did you want to add a little bit more? Yeah.
Do you want to add or do you want to ask?
Ask.
I want to ask.
I want to group B. Why do you use real number into your PowerPoint, but not really calculate it just from the theory?
Can you repeat your question again?
Why do you put real number into your PowerPoint, but not really calculate the velocity of the sound just by the theory?
You mean we didn't calculate the sound by the Reynolds number?
Yes, you don't use real number into
Well,
your
Reynolds number is already calculated by other people, so we can find the information on the internet. There's no need to use it, but we only need to see the relationship, so we can choose the factor we want to change.
I mean is that you don't use real number into your formula, but why do you measure it?
Did you use the constant number in calculating?
You can probably claim it is a constant number, but you don't put it in your formula. It's the point.
Reynolds number is one of the background to understand the fluid. It's the basic knowledge to understand the fluid, how it flows, or how we can see the decay. It's the basic information. We didn't have to use it, but we have to know it first before we did this experiment.
So you can claim that real number is useless for this experiment.
It's not that useless because when we can see that the Reynolds number we can identify the flow we want to see, so we can choose whether the sound speed. So we can see that if the sound speed is higher and it is the turbulent flow, so the decay will be smaller. It will become smaller. So we still use it.
All right, thank you very much.
Thank you. Yeah, I think studying Reynolds is what helped you to set up your experiment. Studying what Reynolds did and reading the book that even a monkey can understand, that's what helped you to set up your experiment. And you had also a very good question.
Yeah, may I add some information for the group B because I think their explanation is good for me because but I think is that the common did you comment? Sorry. Yeah, it's okay. Because I think that both team is very good at the experiment and the research, but the emphasis on different part because they focus on the radius of the tube. Okay, I think they can get good experimental data and the theoretical calculation. But at group B, they just focus on the material. Yeah, but since they think the material is not really affect, but still affect, right? So they just ignore the difference between different materials. And group B, they do the different material, and we can see. In fact, that's not really big difference, but still affect the velocity in the tube. And I think I want to answer the question of the boy here because the viscosity is difficult for us to measure in high school lab, you know, because we try to buy the machine is about 1 million, more than 1 million. I think the good one is the cheap one, maybe 20,000 or 3,000. So we cannot really get the real number. But if you can really measure the real number and the viscosity, we can do much more research on or calculation on the fluid mechanics. Yeah, and that's all. Thank you.
Okay, great, thank you. I think we have some comments from two teachers now also about theme 2. I'm not sure who's going first. Okay. Yes.
Thank you very much for your nice presentation. I think this collaboration is going very well, and I think there are some tips to carry out this experiment. One is how to make sound go through the thin tube. I think it is very hard to go through. And the second is how to measure the time. In Japan, we use the oscilloscope. However, in Taiwan, they use the very simple computer software. It's very good, I think. And third, the selecting a good sound is very important because the sine wave is sometimes not for measuring because the shape is very complicated. And I think you cleared this point. And could you tell me how you clear that point? For example, selecting the sound and measuring the time and making the sound go through the thin tube.
That's a question for both groups, right? Okay. Both of you can answer.
For the sound, we need a loud sound to go through the tube. So we use 2 microphones, and the sound stick, and so we can this machine can know the waves when the waves comes and the wave shape.
What is this machine?
Just the same one, but the same powerful machine. 2 things. And it can know the wave shape and when the wave come, and so we will find 2 waves, and we will know the time between the 2 waves begin, so we can know the time.
Automatically?
Yeah, automatically. And you will know the shape, but because the time is very small, so we need to zoom in and zoom in to know where the. So we can get and so by this machine we can get the similar graph that which is similar to the graph we get from or density or the software you use, and we also need to calculate it by ourselves to calculate the velocity of speed, just in the same way, to find the different time which when two different waves came out, and try to find that difference between the time, and we calculate it, and we use the depth of tube to we use this time to define the depth of tube, so we can get the velocity which runs through the tube.
How about the other group? How did you measure the time?
Just like the teacher said, and in Taiwan we did the experiments by some errors. So like Japan students, they have correct our error because when they did the experiments, they even put the tape over the aluminum pipe or something like that. So make sure it is tight to the earphone. So we can see that, we can know that the sound will go travel through the pipe, not the air outside.
Go ahead.
Thank you. Sorry, in fact I already commented before, but I think this I want to tell everybody. I think this is very amazing for me to see two groups did a great job of this topic, because that topic is very difficult for high school students because the background knowledge is totally did not teach in high school, and you can both get the good paper research and know by yourself to study the advanced courses for the research. I think this is very important purpose. We encourage students to do the research by yourself, and you can learn by yourself. That you can do much more in the future. Yeah, that's all. Thank you.
Thank you very much. Yeah, I'm very, very, very much older than high school students. Very much older. But I do not understand the formulas that you use. But I think it's great that, yeah, as the teacher said, that you are going beyond what you have to do every day in school. And that's where our Japanese students and our Taiwanese students, you guys are pushing the limits, and that's why this is a really, really good project. We didn't learn that. What page is that on in the textbook? I don't know. So you guys really had to research and find it and try things, and I was very happy to see that. That's why this project is great. I'm an English teacher, so I'm going to ask you a quiz question right now, okay? Who said this? Okay. If I have seen further, it is because... Finish the statement for me. It is because...
I stand on the shoulders of giants.
Okay. It is because I have stood on the shoulders of giants. And your answer was Isaac Newton. Isaac Newton said this in a letter. Okay? If I have seen further, it is because I have stood on the shoulders of giants. Now you answered that, many students answered that very fast, so that was in the textbook. Maybe. Okay. Actually, you got the wrong answer. Oh my God. No, you were right. Isaac Newton said that in the 1600s, but if you get back on your favorite website, Wikipedia, you will see that that statement is even older. 12th century, okay? So almost 1,000 years ago, people were saying, oh, the giants came before us, the great people were before us. We stand on their shoulders, we can understand more, we can see further. So it's even older than Isaac Newton. But we still use that, and Newton is very famous for saying that about physics, about science. Okay, so what you're doing, I see this project, what you're doing is standing on some big shoulders. Helmholtz. I don't understand Helmholtz, but he did. His applications are everywhere. And Reynolds is everywhere. And the Lab Quest 2 magic machine that you use to measure waves in electricity, okay? Why don't you research the Lab Quest 2? Who made that? Whose research went into that? Right? It's not magic. It's not magic, yeah. It's a real product of real research from many people, probably many countries. So why don't you check the history of the Lab Quest 2? And you can make the Lab Quest 3. So this project does have a lot of practical application and a lot of vision. You guys can keep going. It should be endless. Science is endless. It's great. I want to say one more thing. I was really, really happy and interested in watching the different groups working because Group A, for example, the train, single train, Group A was more hands-on. You guys were, immediately we said, okay, ready, go. Leo said, okay, ready, start. And you guys started getting the coil and putting the magnet and the battery through the coil, and you tried the angle, and you were measuring the angle immediately. And Group B was doing a different approach. You had kind of a plan set on, you were putting the data in, and you were checking what the Japanese team had done and the Taiwanese team. And eventually, it kind of comes together.